Say I had 5 coins. So I've got 5 coins and there is a 50% chance, so 1 in 2 chance of, for each coin, of getting heads. Okay, how many heads do we expect to get? And the answer is intuitive. You would expect the number of coins that we get, so the number of heads that we get, to be equal to the probability of getting heads times the number of trials, which is 5 tosses. So if the probability of getting heads is 0.5 and we multiply that by 5, we expect around about 2.5 heads per trial. It's impossible to get 2.5 heads. You can't get half a heads. So we would expect that most of the time we would get, say, 2 or 3. Sometimes we would get 1 or 4, and very rarely would we get all 5 coming up as heads or none of them coming up as heads. So let's have a look to see how that would work out if we did that trial 1,000 times. So here I have a simulation that I did before we started here. And what's going to happen is I'm going to get the computer to do this trial 1,000 times, and it's going to toss these coins 5 times in a row. And just interesting there's 5 in a row, just by chance. And it's going to work out the mean number of heads that come up. Okay, so I'm going to toss it 5 times. So the average is 2.521. It's going to toss it another 1,000 times, so we can see there all of the coin tosses. So we see that on average, it comes up around about 2.5 times per trial. So there's some things to note here. The coin tosses are all independent. So the fact that if we take this trial here, first trial, we got tails, the probability of getting heads or tails on the next flip is not going to be altered by the fact that we got tails. So all of these coin tosses are all independent of each other. So we would say that the expected number of an event is going to be the average of that event. And here we can actually see this formally stated for us, where mu is the mean average of the population, and that is equal to the expected number given that trial. Okay, so what do these formulae mean? If you see that there are 2 things being tested here, being worked out here. First one is the expected number, and the second thing is the variance. So the expected number, the E is the expected amount of something. So that's where we expect things to be. The VAR is short for the variance. So this is a test of how spread out we expect things to be. How spread out the results are going to be. So we see here with our coin toss, because the expected outcome was 2.5 heads per 5 head toss trial, we expect the most common numbers we get to be 2 and 3, and for it to be a lot less likely for us to get 4 or 1, and then again a lot less likely again to get 0 or 5. The reason being is there are just more ways of getting 2 or 3 when we toss 5 coins, but in order for us to get 0 or 5, they all have to go the same way. And that's going to be less and less likely as we go on. So let's look at all of these formulae here and see how we would apply them. What does this mean? What does this let's look at the nuts and bolts of this. So the expected value is going to be the long run average number that we expect to get. Okay. So if we were to have a normal 6-sided die, and remember die is one die, and a dice is 2 or more. If we have a normal fair 6-sided dice, what do we expect to get if we roll that? The expected number that we expect to get from that is going to be the average of all the numbers. So that's going to be 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. And if you by 6, you'll get 3.5. Now notice it's impossible to roll a 3.5 on a 6-sided die, a regular one anyway. But if we kept rolling these dice over and over again, the average that we would expect to come out from that is going to be 3.5. So let's just have a look at that and do that very same simulation now. So here I have a simulation set up, and what this is going to do, it's going to roll 1,000 die, and then it's going to add them up and then divide that by 1,000. So I'm going to roll that 1,000 dice, and I don't know whether you can actually see that on the video, but these are all of the results that we get. So if we were to do that by hand, it'd probably take a good hour or so to do that. But the average that we get from that is 3.490, so pretty damn close to 3.5. And we'll do it again. So 3.506, so again, really close. It's to the third decimal place, close. And then 3.494, again, really close. It's 6/1000th off. Not so close, but still pretty close. 3.584, 3.506. We could do this all day. It's very unlikely that we get anything that's much different from 3.5. And we can tell it because the variance is 2.901, which means that it is very unlikely that we get anything that's in the 4s or in the 5s or in the 2s. We could probably do this all day, and we would probably never get anything greater than 3.8 or less, and that's long run expected. So we see here that the mean average is where we expect the result to be. The variance is how spread out we expect that result to be. So let's play a probability game here. Say I owe you $10. And I say to you, instead of that, let's play a game. I'm going to tell you to roll a 6-sided die, I should say. And whatever you roll, I will double that number and add $5 to it. Would you take that bet? What would you need to do? You would need to work out the amount that you expect, and you would do that by using this equation here. So the amount that you expect is going to be aX plus b. I know they have the square brackets here. I should put that in there. So the amount that you expect is going to be $2 times the expected number that you get whenever you flip that die, I should say, plus $5. So what's the expected value of a roll of a dice? We worked that out to be 3.5. Remember, we added them all up together. 1 plus 2 plus 3 plus 4 plus 5 plus 6, and we divided that by 6, and we got 3.5. So the amount that you would expect, given in our bet, is going to be 2 times 3.5 plus 5, and it's going to be 7 plus 5, and it's going to be $12. So depending on how risk averse you are, you would probably take that up. The expected amount that you get back is $12, and I only owe you $10, so you'd probably take that bet if you're a betting person. Because you could roll a 1, in which case you would get $7. But no, it's worth it for you. It's the same thing for any situation like that. And in fact, if we do that 1,000 times, so I've set up a dice transformation simulation here. So if I roll it 1,000 times, and I've got it here to do the dice and then do this little trick here, it's got to work it out for us. So the amount that it did it 1,000 times, the average was 3.404. The variance of the dice here was 2.92. And the mean of the outcome, the payout, is $11.80, which is greater than what you had before. If we did it again, it's going to be $11.94.95, $12, and we're going to round up at 8 cents. Let's say we've got 1 cent coins still. And we keep doing that over and over again. It's going to be very unlikely that if we do that 1,000 times, we're going to get a number which is less than $11.50 or greater than $12.50. We could do it all day if we wanted to. We would probably not find one. I've done it about 20 times and no time it's done that. So you could be fairly certain that your return is going to be greater than $10. So let's look at the variance of our little game here. So remember, the variance measures how spread out we expect the outcome to be, okay, in the long run. So notice that all of the variance is from the coin toss. Remember, we doubled the coin toss. The only thing that's really changing is the amount that we get on the coin toss. If I said to you, I'm going to pay you $5 every time, regardless of what you roll, there's no variance, because a constant, by its definition, has no variance. It's always going to be the same number, so it doesn't change at all. So therefore, the variance of this B number here is going to be 0. And in fact, let's test that. We see here that the variance that we get in this sample is 2.949, and we're not going to go into the mechanics of how we got that just yet. But the variance of Y is going to be 2 times that. So 2 times, let's grab our calculator. So the answer is going to be 2 squared times the variance of the first one there. So the variance should be around about 11.795. So this is the theoretical variance is 11.796, and it's also going to be what we actually got. So this one here is worked out by actually doing the numbers one by one, and this is the theoretical variance, and the theoretical variance is 11.795. We get 11.796. So it's to within 1,000th of $1. So you wouldn't notice the difference. And if we did it again, you'd probably get a slightly different number. But it's going to be fairly close to that number every time. Again, it's probability. You never get exactly what you want, like the Rolling Stones said, but sometimes you get what you need. So just notice the little thing that's here. It's not going to be A, it's going to be A squared. And the reason why is because variance is measured in square units. So remember that the standard deviation is the square root of the variation, mostly It's a simplification, but if you just remember that, then you'll be okay. So if we were finding the standard deviation, then we would use A. But because we're finding the variance, so it's a variance on top of a variance, we need to square that. And what would be the variance of B? The variance of B is going to be 0. So 0 squared is 0. So how do we work this variance out? There's two types of variance. There's population variance and there's sample variance. I'm going to use the sample variance in this case, the population. Actually, no, I'm going to use the population variance. Okay, the population variance. And the variance of that is now going to be the sum. So all of the numbers added up. So it's going to be the sum of all the numbers added up minus the mean of that squared all over the number of numbers. So just to show you that the B bit doesn't change the variation. Say we have 5 numbers, 1, 2, 3, 4, and 5. And I asked you what the variance of that would be. We would need to find the population mean. Let's say there's a population of 5. And it's obviously, it's going to be 3. So 2 plus 1 plus 2 plus 3 plus 4 plus 5. Added up together, we're going to get 3. So our variance of this little subset here is going to be 1 minus 3 squared plus 2 minus 3 squared plus 3 minus 3 squared. Going to be pretty easy to work that one out. Plus 4 minus 3 squared plus 5 minus 3 squared, all divided by 5. So let's work it out. So 1 minus 3 is 2 squared, so that's going to be 4. 2 minus 3 is minus 1, so that's going to be 1. 3 minus 3 is 0 squared, so 0 squared is 0. 4 minus 3 is 1, so it's going to be 1. And 5 minus 3 is positive 2, so 2 squared is going to be 4. And if we add those up together, 5, 10. So it's going to be 10 over 5, so the variance is going to be 5. Okay, so I've got the numbers here, 1, 2, 3, 4, and 5. What is the average? I'm going to say the population. I know it really should be X bar, but I'm going to say mu. The average, the population average is 3, and the variance is 2. Okay, now let's look at the numbers 101, 102, 103, 104, and 105. I invite you to go and find the mean and the variance of that sample. And when you do, you'll see that the average is 103, but the variance is still 2 again. Remember, the variance is how spread out they are. The mean is the average. So adding 100 to these numbers changes the mean, but it doesn't change the variance because there's 5 of them within 5 points of each other. For this last pair of formulae, I just want to do that again by using a game. So say I say to you, you can roll 2 dice, okay, and I'm going to pay you the following. I'm going to pay you $2 or whatever comes up on the first die, plus $3 for whatever comes up on the second die. How much would you expect to get from that? The amount that you expect from $2 times whatever you get in the first one plus $3 times whatever you got on the second roll is going to be $2 times the expected number of on your first dice plus $3 times the expected number on your second dice. So X is the first dice and Y is the second dice. So notice here that these dice are independent. They're not talking to each other. They're not saying if you come up 3, I'll come up 5, or let's both of us come up on 1. They're not doing that. They're not affecting each other, so they are independent. How much are you going to expect to make? We know because they're independent and because we've already tested it, that the expected number for each is going to be 3.5. Remember, we already worked that out. So our expected amount we are going to get is going to be 2 times 3.5 plus 3 times 3.5. So let's grab our calculator and work out what that is. So 2 times 3.5 plus 3 times 3.5 is going to be $17.50. Let's do that in a simulation just to show that this actually does work. So here I have another simulation. I'm going to roll 2 dice 1,000 times, and the payout will be $2 times the first die plus $3 times the second die. So the payout is going to be 2 times the first plus 3 times the second. And I have the numbers for the first die, the second die, and combined for our payout. And I'm going to roll 1,000 times. And hey presto, it gives it to us 1,000 times here in all of its gory detail. Again, if you were to do that by hand, wow, that would take you a long time to do that. So the mean of the first die came out to be 3.564. Okay. The mean of the second one, oh, that's nice. It came out to be exactly 3.5. That's pretty rare itself. And our mean payout is $17.63. Remember, we have to round it to the nearest cent. And the variance of this payout is 37.93. And that's pretty much all that means. So let's have a look at how we would find the variance for that and the mean for that. We've already got the mean for that, but the variance is going to be pretty much the same as before. The only thing which is going to affect it is going to be that now the amount that we pay is going to be squared. And the reason being is that variance is in square units. Mostly when you deal in statistics, you're talking about standard deviation, and the rule of thumb is the standard deviation is the square root of the variance. It's a little bit more complicated than that, but we have to square it. So the variance, once we've worked it out, of the whole thing is going to be equal to 2 squared times the variance of the first die plus 3 squared times the variance of the second die. And it's going to be pretty close to that in our set. So let's have a look at the actual numbers that we get. The numbers we got were 3.564, 2.93, 3.5, 2.99, and that. So let's test out to see whether that actually does work. So the first die, the variation of the first die was 2.930 plus 9 times the variation of the second die was 2.9. So in total, that comes to 4 times 2.99, 38.63. So variation doesn't have a unit, it's just the number itself. Think of this as kind of variation units. So how close is that to the actual variation when we did our simulation? We got the variance of 37.9, and We got fairly close. There is something there which is missing, but we're going to get to that later. I just want you to look at the mechanics of how we get that and how they're related. And I'll leave it at that. So where is there a difference? The difference in the variation is due to the fact that any small differentiation from the theoretical variance to the actual variance that we measure, and remember that variance that we measure is going to change a lot, is going to be amplified because now it's times these numbers here. So 9 times any small error plus 4 times any small error, it's going to compound. Maybe that clears that up.